Hello and welcome, I'm James Murphy, and today we're talking about the MD5 hashing algorithm. MD5 stands for Message Digest 5, and what it does is it takes in a message and outputs a summary, called a digest, of the message. Change the message by even one character, and the digest is supposed to be completely different. The message can be any length, but the digest will always be exactly 128 bits, which we think of as 4 32-bit integers. MD5 is what's called a hash function, which really just means it takes messages of any length to a fixed length. But MD5 wasn't intended to just be a hash function, it was intended to be a secure hash function. Among other things, you aren't supposed to be able to find inputs with a given hash, or even two inputs with the same hash. Unfortunately, MD5 is not a secure hash function. It's completely broken for cryptographic use. But it's still important from a historical perspective, so let's take a look at it, see an implementation of it, and then discuss some real-world attacks against it. But before we do you know who's not going to use a broken hash function like MD5? Today's sponsor, Hostinger. Try Hostinger's premium shared hosting plan, which has 99.9% guaranteed uptime, one free domain and free SSL certificate, and a 30-day money-back guarantee. Use coupon code MCODING in all caps at checkout to get up to 91% off on all yearly plans. Okay, so let's just dive into the code. What I have here is an implementation of the MD5 algorithm. The first thing that we need to do is decide what does MD5 take in and what does it spit out. So what I decided is that we're taking in bytes and we're spitting out bytes. The way that we're going to do this is basically we make a state object, which is going to keep track of all the information of the algorithm. We feed in whatever bytes that we have, and then we're going to have to do some finalization. And the reason for this is because the MD5 works on blocks that are 512 bits long, 64 bytes. So if your input string was not the correct length, then it has to get padded. And that's going to happen in this finalization step. So down here I have basically the same thing, but instead I'm directly passing in a file handle. We see that the MD5 state object is keeping track of four things. The most important one is this state variable. At the end, this state is going to be what is ultimately made into the digest. The way that MD5 works is it operates on chunks of 512 bits at a time. So the first thing is that, of course, we need to take in exactly 64 bytes, and then we convert those bytes to integers. So we take the whole chunk and we convert 64 bytes into 16 integers. Then we start with the process of updating the state. So we have four variables, A, B, C, D, that make up our state variable. Then we're going to go through 64 times and basically mix in the message in a particular way. So the general way that this works is for each of the 64 steps, there is a mixer for that step that's going to mix up bits. And then we're also going to mix up which of the bytes that we use from the message. The 64 steps of the algorithm are split into 4 rounds of 16. In the first round, we use the F mixer. In the second round, we use the G mixer, third round H mixer, fourth round I mixer. So this mixer for step whatever is going to just tell you which of the F, G, H, I is going to be used for that step in the algorithm. Similarly, we're not going to read the message in order. And so in the first round, you read the 16 integers in this order. In the second round, we read it in a different order. And so we take the mixer for a given step and we take the index, which integer do we want to read from the message at each step, and we just put both of those into big lists so that for every step we know which int we're supposed to be reading out of this array and which mixing function we're supposed to use. So for all 64 steps, we pick the correct mixer, we pick the correct index for the message that we're supposed to be using, and then we just use this formula. We take A and then we throw B, C, and D in with the mixer and then add that in. And then we add the message at the specified index in, and then we add in this sign randomness. This is just another thing that's just thrown in just because the algorithm says to. Okay, so back to the main loop. We mix our bits, we rotate our bits, then we add A to B, and then we rotate. We take A, B, C, D, and you can see we take the D and we put it in the front here, so then we have D, A, B, C. That's all there is to it. After we mix all of our bits up in this way 64 times, then whatever our state variables are now, we add them to what they were at the beginning. So how do we ensure that we actually do this for every 512 bits in the message? Well, that's what the process function is for. So here's what we do in a loop. We try to read however many bytes it takes to fill up our buffer and make a full block size number of bytes. If our buffer was empty before and then I read in a full block size, then I just go ahead and call compress on the buffer and then increase the length. Otherwise, I already had some bytes in my buffer, or I didn't read enough bytes in order to fill up the buffer. So what I do in that case is I note that, I've now filled up more bytes. And if I filled up now enough to do a compression, if I filled up the whole buffer, then I go ahead and compress and increase the length and then set the number of filled bytes back to 0. Otherwise, I still haven't read enough bytes in order to do another compression. So I just keep reading bytes until I get to the end of the stream. But what happens when I get to the end of the stream and I've read some bytes, but not enough to fill up the entire 512 bits to use a compression on it? Well, then we use this finalize method to basically pad the end. What we have to do is we append a 1 bit onto the end of the message, and then we pad it with zeros. In all cases, we're going to pad with zeros and append the length of the message that we just read as a 64-bit integer onto the end of the message. But if adding that length onto the end is going to overflow the block size, then we actually need to do an extra compression. So we might have to add on more zeros, compress, and then add on the length. But in any case, we're basically just padding with exactly enough zeros so that once we get to the end of the message, we can add on our 1 bit, our 0 padding, and then our 8 bytes representing the length, so that it comes out exactly to a multiple of 512 bits, and we do one last compression. Once we finalize the message, then we just need to output the digest or hex digest. And the way this works is it's literally just these state variables, whatever we updated them to, that's now what we output as the digest. So why do we say that MD5 is a completely broken hash function, at least for cryptographic purposes? Well, it's susceptible to a number of attacks. And for one, here is a collision. Here's 2 different messages that have the exact same MD5 hash. I know they look very, very similar, and they are, but they actually differ in 2 places, 0002 and D5 versus 55. There are a bunch of different types of attacks against hash algorithms. If you say you have a collision attack against a hashing algorithm, then you're just saying you're in the situation like I showed before with these 2 messages, where you just have 2 different messages that have the same hash. And that's not necessarily that useful for an exploit. What would be more useful to an attacker is something like a chosen prefix attack. It's given this name because you can pick any 2 prefixes you want, like this one says, launch the nukes, and this one says, don't launch the nukes. And then you can add on extra bytes, different sets of bytes to those 2 messages, and then whatever suffix you want after that, such that those 2 things have the same hash. Already in the real world, there have been several instances where either researchers or real hackers were able to use something like a chosen prefix attack on MD5. One instance, they had a Microsoft code signature for one of their binaries, and they had Microsoft sign something that was completely innocuous, but that completely innocuous thing had the same MD5 hash as a virus. So whenever you're allowed to control the prefixes like that, that's the case where you can really start doing some damage. Okay, so these last 2 attacks are just theoretical. For MD5, there's no publicly known actual implementation that can do either of these things. So a second preimage attack is basically you've got a file or a message that already exists, and you want to find another message with the same hash. You can imagine you have an operating system, a Linux image that lots of people are downloading, and a hacker could switch it out for a different image that has the same hash. And a full pre-image attack is basically the same thing, but you don't even need the file. All you need is the hash of the file. And that's all I've got. Thanks for making it to the end. Don't forget to like, comment, subscribe, and check out our sponsor in the link below.